started, everyone. When you click over to the front page, you know that we only have 2 weeks to go, and we have 4 sections to do, and I can't remember what number the section is, so I left the number blank. But the first section, the first of these sections is going to be a thing called Coral and Div. I'm going to show you like a 6-minute video on it. It's a very visual thing, and I'd like to show you that, or at least attempt to. So that'll be the first thing today, and then after that we can get into what all this stuff is. I guess I should hide right now. It's more of a distraction than a help. And so that's the goal. So we're going to look at the 2 processes, 2 things that you can do, called finding the curl of a vector field and finding the div of a vector field. And these do get used in physics. I've been verified, but I'm sure engineering, electrical engineering as well, all of them, the higher level stuff, use these processes operators to describe physical things in their field. So it's a pretty big thing. So let's stop that share, and I'm now going to get into the dangerous place where, okay, oops, Isaiah just came in, got distracted. You cannot distract me. It's not a good idea. Right, here goes. I'm going to try and show you a video which I will put up online in Canvas if you want to see it again. It's a really cool one, I think, anyway. And it kind of tells you what divergence and curl is, rather than just this is how you get it and then you don't know what you've got. So, fingers crossed.
I are going to get into divergence and curl. To make sure we're all on the same page, let's begin by talking about vector fields. Essentially, a vector field is what you get if you associate each point in space with a vector, some magnitude and direction. Maybe those vectors represent the velocities of particles of fluid at each point in space, or maybe they represent the force of gravity at many different points in space, or maybe a magnetic field strength. Quick note on drawing these, often if you were to draw the vectors to scale, the longer ones end up just cluttering up the whole thing. So it's common to basically lie a little and artificially shorten ones that are too long, maybe using color to give some vague sense of length. Now in principle, vector fields in physics might change over time. In almost all real-world fluid flow, the velocities of particles in a given region of space will change over time in response to the surrounding context. Wind is not a constant, it comes in gusts. An electric field changes as the charged particles characterizing it move around. But here, we'll just be looking at static vector fields, which maybe you think of as describing a steady-state system. Also, while such vectors could in principle be 3-dimensional, or even higher, we're just going to be looking at 2 dimensions. An important idea, which regularly goes unsaid, is that you can often understand a vector field which represents one physical phenomenon better by imagining what if it represented a different physical phenomenon? What if these vectors describing gravitational force instead defined a fluid flow? What would that flow look like? And what can the properties of that flow tell us about the original gravitational force? And what if the vectors defining a fluid flow were thought of as describing the downhill direction of a certain hill? Does such a hill even exist? And if so, what does it tell us about the original flow? These sorts of questions can be surprisingly helpful. For example, the ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field. Here, take a look at this vector field, and think of each vector as describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness, as if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness. The divergence of a vector field at a particular point of the plane tells you how much this imagined fluid tends to flow out of or into small regions near it. For example, the divergence of our vector field, evaluated at all of those points that act like sources, will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction, since that would still insinuate a certain spontaneous generation. Now on the flip side, if in a small region around a point there seems to be more fluid flowing into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in two-dimensional inputs and spits out two-dimensional outputs. The divergence of that vector field gives you a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative, and that output is just a single number, measuring how much that point acts as a source or a sink. I'm purposefully delaying discussion of computations here. The understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one used to illustrate an arbitrary vector field, then if that fluid is incompressible, the velocity vector field must have a divergence of 0 everywhere. That's an important constraint on what kinds of vector fields could solve real-world fluid flow problems. For the curl at a given point, you also think about the fluid flow around it, but this time, you ask how much that fluid tends to rotate around the point. As in, if you were to drop a twig in the fluid at that point, somehow fixing its center in place, would it tend to spin around? Regions where that rotation is clockwise are said to have positive curl, and regions where it's counterclockwise have negative curl. And it doesn't have to be that all of the vectors around the input are pointing counterclockwise or all of them are pointing clockwise. A point inside a region like this one, for example, would also have non-zero curl, since the flow is slow at the bottom, but quick up top, resulting in a net clockwise influence. And really, true proper curl is a three-dimensional idea, one where you associate each point in 3D space with a new vector characterizing the rotation around that point according to a certain right-hand rule. And I have plenty of content from my time at Khan Academy describing this in more detail if you want, but for our main purpose, I'll just be referring to the two-dimensional variant of curl, which associates each point in 2D space with a single number rather than a new vector. As I said, even though these intuitions are given in the context of fluid flow, both of these ideas are significant for other sorts of vector fields. One very important example is how electricity and magnetism are described by 4 special equations. These are known as Maxwell's equations, and they're written in the language of divergence and curl. This top one, for example, is Gauss's law, stating that the divergence of an electric field at a given point is proportional to the charge density at that point. Unpacking the intuition for this, you might imagine positively charged regions as acting like sources of some imagined fluid, and negatively charged regions as being the sinks of that fluid. And throughout parts of space where there is no charge, the fluid would be flowing incompressibly, just like water. Of course, there's not some literal electric fluid, but it's a very useful and a very pretty way to read an equation like this. Similarly, another important equation is that the divergence of the magnetic field is 0 everywhere. And you can understand that by saying that if the field represents a fluid flow, that fluid would be incompressible, with no sources and no sinks. It acts just like water. This also has the interpretation that magnetic monopoles, something that acts just like a north or a south end of a magnet in isolation, don't exist. There's nothing analogous to positive and negative charges in an electric field. Likewise, the last 2 equations tell us that the way that one of these fields changes depends on the curl of the other field. And really, this is a purely 3-dimensional idea, and a little outside of our main focus here. But the point is that divergence and curl arise in contexts that are unrelated to flow. And side note, the back and forth from these last 2 equations is what gives rise to light waves. And quite often, these ideas are useful in contexts which don't even seem spatial in nature at first.
That is a cool video. I don't know how cool it was for you, but I really like it.
What was the video?
What do you mean, what was it?
Well, what was it called on YouTube and who was the author?
Oh, I'm going to just copy it and put it on Canvas and you can get it.
Oh, fantastic.
right? There's more stuff after that, but well, we have a lesson and we have to do stuff, but it's really cool. How you get the concept that these two things, although you don't know yet how to calculate them, are biggies, right? They are kind of the skeleton upon which anything to do with magnetism, electricity, light. I mean, a lot of the physics in this world end up being described using these things called curl and div, right? So I'm trying to show you on the big picture here, right? They're important. Now, what are we going to do? Well, we're a calc class, so we're not going to do physics. That's what physics class do. So we're just going to show you how to calculate these things. But hopefully it'll feel a little bit better that you say, okay, there's a reason why I would want to do it, right? So let's show you how to do it. Well, yes, I will show you how to do it, but I have to show you some other stuff first.
So a given vector here is telling you
Oops, sorry.
how and how quickly
Okay,
a given pair of population sizes tends to change. Notice, this is a case where the vector field is not about physical space, but instead it's a representation.
There he is. Don't know how I did that, but I was about to praise myself by saying I made it work, which I kind of did. I just don't know how to shut it off without closing it. Okay, so we will do it, and it's under here, but I need to show you thing. It's called an operator. Right, what is an operator? Well, you already know one. You remember this fella?
Of course.
Right, it's a great grad guy. You remember him? Yeah. He's an operator. At least this piece is. And an operator, and this is the only one we're going to be dealing with, is that. It's basically a process. So if you do delta of f, you do this process with a function f. Right. So keep that guy in mind. Right then. Let's show you. Yeah, I'll use my notes. I've got them here, but that way at least I won't screw them up. The first one we're going to look at is how to calculate the divergence. And you always find the divergence of a vector field. And we'll have the vector field be capital F, and we'll keep the textbook. We'll call them P, Q, and R again. Well, the divergence of a vector field is the dot product of the delta operator with the vector field. As a function, it looks like this. You see that that's a scalar. That's a single thing. It's not got a dimension. It's not got little funny brackets, comma, and so on. And that fella is what we call the divergence. And it's normally written as div f.
Okay.
Surprisingly simple formula. You thought, based on what these things do, this would be quite a weird and messy one, right? But it's not really, is it? I mean, it's just the partial derivative of this with x added to the partial derivative of y with this, added to the partial derivative of r with z. Now, it's not the same as this fella. If you were going to get this fella, don't you end up with a vector? You see, it works differently. But it is a very useful notation to think of delta as being an operator. It just allows us to do the div in that form. And if we know how to make it happen, it really does work. I wouldn't normally do this, but just to show you how it would work. What we're doing is the dot product of this guy with this. Now, normally when you do dot products, don't you multiply this term by this? Instead of thinking of multiplying, can you think of this guy operating on this? Can you see where that comes from? And then you add this operating on that, probably why it's called an operator, and this operating on that. Are we cool with the div? Pretty easy thing to calculate, actually, considering how important it is to find it. I'll do an example. Two xy, x squared y, x squared y, z cubed. If I wanted to find the div of this three-dimensional function, I would differentiate this, because that's basically p, this is q, and this is r. I would differentiate p with x. Whoops, forget that bracket, it's not there. Add that one, and then add that one. So what would I get? I'd get a 2y out of that term, get an x squared out of that term, and I'd get a 3x squared y z squared out of that term. Would you agree it's not the hardest thing that we've ever done? It's just three partial derivatives put together. Any questions about calculating the div? You feel as long as I tell you who f is and say find div of f, you'll be cool. Okay, move on. How about the curl of f? Right. Well, this is the formula . It's the cross product of delta and f rather than the dot product of delta and f. Now, you have to set it up as an ijk again. We're used to doing that. And the delta operator goes in the middle. And then f, which is p, q, and r goes at the end. So the curl of f is this determinant, right? This three, in this case, 3 by 3 determinant. So it's going to be so many i's, take away so many j's, add so many k's. So if I kind of cover up the i's, let's see what we get. This operating on that, take away this operating on that. So d by dy of r, right? Take away dq by dz. Then you move to the middle one, this operating on that. Take away that guy. And finally this one, dq by dx, take away dp dy. Now you might see, in fact, I'm sure you will see, this formula as the formula for calculating the curl of f. Would you agree that it's probably not a formula you want to memorize? Isn't it just much cleaner to memorize the 3x3 vectors that you're going to get the determinant of? Right. So doesn't this notation using the operator delta make the curl of f a lot cleaner than what it looks like if you write it out in a more algebraic form? Although they're exactly the same thing. I mean, just to me anyway, doesn't that look cleaner? It's easier to do. So let's do an example of that. 3xy, x squared plus z squared, x squared plus y squared, take away z squared. And I would like to find the curl of that guy. So the curl of this vector field is going to be I, j, k. My operator. Hold on a second. How am I going to do this? I can never do things when I want them. There we go. Be back in a second. Here we go. Put in the operator now. Essentially, this row is the operator for delta, and P is 3xy, Q is x squared plus z squared, and Z is x squared plus y squared, take away z squared. So it's going to be so many i's, take away so many j's, plus so many k's. Okay, watch me because I'm probably going to screw up here. I'll try my best not to. Okay, cover that guy up. You differentiate this with respect to y, you get 2y. Take away, you differentiate this direction with respect to z, 2z. Does that look good? 2y, take away 2z. If you make a mistake, you shout. Middle one now. With x's, you get 2x, take away. Well, if you do this with y, you just get nothing. And the third one, if you're going this way, with x's, you get 2x, take away, going this way, 3x. Then you make it look pretty. 2y, take away 2z, comma, negative 2x, comma, negative 1x. We now have our curl. And you notice that the curl is a three-dimensional vector. And if you're wondering what does a curl look like in a 2D world, isn't it just a determinant of that vector? Whoops. So it's basically that guy, take away that guy. You don't need the i's and j's, right? You just go. So that's when he was doing the 2D picture and he was saying the curl was 4 or the curl was negative 4. For a 2D, it would just be this derivative, take away that derivative, which would essentially be that guy. Well, actually, there wouldn't be any z's in it because it's two-dimensional. But it would be that guy, take away that guy.
Professor, would you mind redoing the I again?
The I again? Coming up.
Yes.
You differentiate this fellow with respect to y, and you get 2y. Take away this guy with respect to z, which is 2z. So 2y,
okay.
Take away 2z.
I see it now. I wrote it down wrong. Okay.
We go?
Yeah.
Right, so we'll get practice at this, so don't think this is the only time you're going to see one example done. But when you're looking at calculating the curl of f, if I give you f, do you feel that you could set up basically, that's your template, isn't it? That's not going to change. Doesn't that just become p, q, and r? Right? And you do the usual stuff that you need to do. Here's a guy that we've met before. If F is a conservative field, well, do you know if the curl of F is a zero vector? See if this guy that I just calculated was 0, 0, 0, right? You imagine it might happen, right? So the curl of F is a zero vector, then the vector field F is a conservative field. Now, when we did conservative fields, didn't we just do the 2D test? Can you remember the 2D test?
Yeah.
Right. Now, if you want to see where that 2D test comes from, let's pause for a minute. Then you're only going to do a vector field made up of two pieces, right? So it's a 2D one. And when you do the curl of that, the formula changes a little bit. The only guys that you need are the operators in P and Q. Right? You don't need the I's and J's when you do 2D. And can you see? Remember the test? Doesn't that need to be 0 to be a conservative field? And I think I remember saying to you something along the lines of, you know, you can do it for 3D, but you do not want to see the formula for it. I don't know if you are that scared of it anymore, because don't we now know the formula for it? In fact, now that we have a test, right, you are a conservative field if your curl is 0, and there's a few other things, but mostly that's the major one. Can't you do that with a fourth dimensional vector? Right, you just find its curl, and if it's a 0 vector, it's a conservative field. And if you're a conservative field, you have a potential function. And the fundamental theorem of line integrals can then be used. So I think it's kind of interesting. Any questions about the curl? Is it cool? Curls and divs. Here's a property. I'll put brackets around it. If you are a well-behaved vector function, vector field, F, what do you think the div of your curl will be? Lots of things or one thing? Any gut feeling?
Shouldn't that be 0?
Yes, it will be. Interesting property. Not sure what it tells me, but evidently it's just.
So that's if F is conservative.
If I believe it works for any function, even if it's not conservative. But it's certainly true if it is conservative. But it's actually true for any well-behaved function. Now, the reason I'm saying well-behaved, there are some weird functions out there where nothing behaves the way it should. I think the closest word I'll put to it is, can we call it a continuous function? Right, nothing weird's going on, right? Like a continuous vector field. This is true. So it doesn't even need to be conservative. But conservatives, it does work for, because that's 0, isn't it? And what's the div of 0, 0, 0? Of course it would be 0. But this is true even if F is not conservative. It just needs to be well behaved. So if you found a function and you did this and it wasn't the number 0, you would be saying, I do not like this vector field. It is misbehaving. I should be very, very careful when I do any computations using it. Because if it's not well behaved, then weird things do and can happen. And we don't like misbehaving functions, do we? We like ones that do what they should do. Okay, let's pause a minute, because I need to set up some stuff. I thought I had done it, but okay. Where are you hiding? I wonder if I closed it by mistake. Right, I'm just going to go in and pick some homework questions, or at least ones like it. It's just safer. Although really, because I'm differentiating, it's not that dangerous. I can make up ones. But at least it'll give us an idea of the quality of questions that you're likely to experience. Now, while this thing is getting ready, can I remind you that your final, well, you've got one more test that's coming up, but I should remind you your final will not be on WebAssist. Your final will be a PDF that will appear on Canvas, and you will just write the answers down on paper and use Adobe Scan and send it to me. So it's much more like a normal test. Right? And there is a practice one that I have that I will send to you nearer the time. And it'll give you an idea of what's going to be expected of you. The finals, because that's what finals are, will be much harder because you're trying to remember 10 weeks work instead of 2, and it's just easier to do. A little heads up. Okay, I'm ready. So, well, let's show you what they look like. This is what the kind of thing you're going to be asked to do in the homework. All sorts of things floating around here. Go away. There we go. Maybe make this a little bit bigger. A lot of questions, I want the answers. Stop doing that, it's distracting. Go away, there we go. Here's your vector field, find a curl, find a div, right? Pretty straightforward questions. Here's your vector field, find a curl and div. Find a curl and div. Now, in question 4, determine whether the vector field is conservative. Now, won't that be, you will find the curl of f and show that it's 0, right? The 0 vector. And then when it is, can you remember doing that find little f? Remember how we did that? Delta f equals capital F, and then you pair off the d by dx, the d by dy, and the d by dz, and integrate with, what was that better word that someone should? Not combine, but
Merge.
What was it? Say again, Vince.
Merge.
Merge, that's it. And you merge them together to get a little f. So you're basically going to find the potential function. So first you're proving that the curl is 0, and then you're going to do some stuff you've done before, right? Find the potential function, little f of x, y, z. Mostly 3D as you'd expect. Same thing there. Same thing there. Back to finding curls and divs. Plenty of practice. I figure out that something that's as important as this, you need plenty of practice so you're good at it. That one I'll probably do later. Yeah, okay. So they're not a lot of variation. They're really just 2 kinds of questions. First kind says, here's a vector field at capital F, find the curl and div. And the second question is, prove that this vector field F is conservative and find the potential function little f. So let me pick one at random. This is similar to question 1. So I'll move over to the whiteboard. And this fella is x, y squared, z squared, pretty much x, y, z squared, x squared, y squared, z. And we're going to find a curl, we're going to find a div. Right, to get the curl, Right, we'll do the cross product one. It's going to be I, J. Okay. We'll put in our operators, our delta operator, and then P, which is this guy, Q, which is this guy, and R, which is this guy. And it's going to be so many I's, take away so many J's, plus so many K's. Okay, watch me for screwing up here. You do this operator, you get 2x squared yz, take away what? 2x squared yz. Oh, that's nice. Move on to the middle one. If you do this one, you'll get 2x y squared z, take away 2x y squared z. And the last one, if you go this way, you will get 2x yz squared, take away 2x y z squared. I know I can't write very fast, very small. Oh, isn't that a cool one?
Is that like a symmetry thing or something?
Well, the curl of F means that we have a conservative field. I think in this particular case, it kind of worked because there was a lot of symmetry in the function, but you can get conservative fields that are asymmetric, right? They're not symmetric. Although I would guess if you were a symmetric thing, you'd probably be conservative, but being conservative doesn't mean you need to be symmetric. It does mean it's a conservative field, right? If you think of it in the 2D world, isn't that curl how much it's going to try and turn anti-clockwise or clockwise? And when you go into 3D, it's a little bit more complicated than that. But a conservative field basically has no, try to think of a verb here, has no overall curvature in it, right? It's not like a cyclone, right? Like there's a big turning thing happening, right? Right, now if you want to get the div of F, it's our operator dot product with F. And our operator looks like this. And I'm just going to say F because it's too big. So what do I get? I get differentiate this fellow with respect to X. Add differentiate this fella with respect to Y. Add differentiate this fella. And you get that. This particular question didn't ask it, but haven't I just proved that this particular vector field is a conservative field? It wasn't what I was asked to prove. I was just asked to find these two things. But indirectly, haven't I proved that it's a conservative field? Now, since it is, let's pretend that there was a part C and it said, find the potential function little f of xy. So if you are a conservative field, isn't that true? And this guy is df by dx, comma, df by dy, comma, df by dz, right? Our typical grad. And it is going to equal this guy, and finally, that guy. So when we match them up, the first one needs to equal this. The middle one says that this needs to equal that. And the third and final one says this has to equal that. So we're doing stuff we've done before, right? We are trying to find little f, the potential function little f. So remember what we do here, don't we just integrate this with respect to x? Now, if you integrate this function with respect to x, you get 1/3 x cubed y squared. Okay, I apologize, nobody caught it. That's an x. That's just an x transferred. Same thing, but you're going to get 1/2 x squared y squared z squared plus an arbitrary constant that doesn't have an x in it. And if you do this one with respect to y, you're going to get 1/2 x squared y squared z squared plus an arbitrary function that doesn't have any y's in it. And if you integrate this one with respect to z, you get that guy plus an arbitrary constant that doesn't have any z's in it. And I think we got lucky here. Would you agree that little f is, when you merge them, is that guy? And since this is our potential function, as it's called, not that I'm going to do it, couldn't I do any line integral I possibly wanted? Because won't it just be the potential function at the end and the potential function at the start? So I just need to evaluate the space curve at A and at B and plug them in here and here, and then the potential function will do the rest for us. So it's a kind of nice little loop, isn't it? That you have curls, in this case curls, tell you that you've now got a conservative field. Conservative field then means you can find a potential function. Finding a potential function means you can now simplify a line integral question down to simply just evaluating the potential function at the start and finish of the curve. That is cool stuff, isn't it? The whole package. Any questions? Because this is a nice point for us to finish, I think, today. Right, say hi, everyone. I don't know the answer to this, but I think I got a good question. If the curl of f is a zero vector, means you've got conservative field. What does the div of f equal 0? Because remember, the div of f is a scalar, right? What does that tell you?
Will that say that actually no, I'm not sure.
I don't know either.
I'm not sure.
I have a good question, but no answer. Anybody in physics, what would a divergence of 0 everywhere on a vector field tell you? There were no sinks, and there's no, whatever the other words, right? There's no places where it's coming in, and there's no places where it's going out.